Thank you very much, Elena. And it is really a pleasure to be here. Amsterdam is the first city that my wife and I traveled to in Europe after we got married, so coming back here brings back so many fond memories, and we just love it. And I appreciate being here with my esteemed colleague, Sebastian. So I am a defensive researcher in Intel Labs. My name is Scott Constable. This is Sebastian Österlund. He's an offensive researcher in the Intel Storm team. And we also have some of our own thanks to give. Thanks to the rest of our team, Peter Zelstra, who's a Linux kernel engineer, and Alyssa Milburn, who's another member of IPAS Storm. She couldn't be here today, but she's also local. And to Joao Moreira, who's one of the original authors of FineIBT, and he gave us a lot of helpful feedback, and also to many other people throughout Intel who helped to provide valuable feedback and insights as we developed what we're about to present today. And finally, one thank you to the Linux kernel community who really helped to refine this enhancement throughout a very lively discussion in the Linux kernel mailing list, and I think it became a lot better as a result, and it was very productive, and I learned a lot. So thank you very much. You're a tremendous community. Yeah, sure. Give yourselves a round of applause. Absolutely. Yeah, you deserve it. And in addition to the disclaimers up here, Sebastian and I have some of our own disclaimers. We will shamelessly and unapologetically be using the Intel assembly syntax throughout this presentation. It is the correct one, the one that, remember, assignments move from right to left, just like in your favorite programming languages, so that's the right one to use. Never forget that. So what we're going to be talking about today is addressing a problem that I hope that many in the security community are very familiar with, call-oriented programming, or an adversary doing something to redirect an indirect function call from the correct or the intended target, say F, to a maliciously chosen target, something else, G. And by redirecting the function call, something bad is going to happen, and that's what the attacker wants to do. So this is a very old problem, a problem that's been revisited many times, and that we are revisiting today with a sort of new approach. This problem comes with two faces in the Linux kernel. So one is the classical, the architectural side of it, where you might have, say, a buffer overflow or a use after free that results in a pointer being corrupted, and then that pointer becomes something that an adversary crafts into the malicious target, and then that can be redirected maybe to do privilege escalation or some other benevolent activity. The other side that has come into focus since the beginning of 2018 is the microarchitectural side. And I'm talking about the Spectre family of vulnerabilities, and in particular in this talk we're going to focus on the Spectre family of vulnerabilities that target indirect branch misprediction. On the architecture side, there's a solution that has been adopted that was merged, I believe, all the way back in Linux 6.2, at least if you're compiling with the Clang LLVM tool chain and running on Intel hardware, that is called FineIBT. And FineIBT is a fine-grained forward-edge control flow enforcement technique that combines software approach with a hardware ISA extension introduced by Intel called CETIBT. It uses that to enforce fine-grained forward-edge CFI. But on the microarchitectural side, the story is far less tidy. There's no unified solution. There's a variety of knobs and bits in little MSRs that are scattered throughout by different hardware vendors who define them a little bit differently from one another. There's a lot of platform-specific behavior, a lot of hardware vendor-specific behavior, and it's really difficult to navigate if you're not deeply familiar with the literature on side channel vulnerabilities or speculative execution vulnerabilities. What we'd like to show you today is the steps that we are taking toward introducing a unified solution that enforces forward edge, fine-grained CFI at both the architectural level and the microarchitectural level, so that at some point in the future, we will no longer have to rely on a variety of bits and MSRs and ad hoc techniques that apply to some parts but not others. So that's what we'd like to talk about today. And Sebastian's going to get us started by taking us a little bit deeper into the background on the vulnerabilities we aim to address.
So yeah, thanks, Scott, for that. I think Scott set the stage for what we're going to talk about today. So let's start with some light morning material Spectre. As you might have known, there's a bunch of different variants. These microarchitectural attacks came up a few years ago, and we have seen more and more variants popping up over time. Today, I want to address specifically Spectre variant 2, also known as Spectre BTI, or branch target injection. With Spectre BTI, an attacker can inject a target for indirect call, which will be executed speculatively by some kind of, you could see it as a confused deputy attack. So someone traces the branch predictor to target a certain so-called gadget that does whatever the attacker wants to do, and then they exfiltrate it through some kind of cache attack, for example. I'll go a bit more into detail of this in a bit. Of course, there's multiple variants, like this one, for example, was mitigated with some things that we'll talk about in a bit. Then some of these people came up with some new variants of Spectre that can bypass the mitigations, for example, Spectre BHI, where you actually modify the branch histories. You don't actively target what the indirect call target can be speculatively, but you change the history so that it actually speculatively targets so some kind of known target chosen by the attacker. It will be a bit more clear in a bit. Another consideration is that we have this nice thing called eBPF in the kernel, which is kind of a virtual machine running in ring 0, which for these kind of things is a really hard thing to mitigate, right? If you have a user that can run arbitrary code in ring 0, these kind of mitigations become really, really hard to deploy. So on the mitigation side, as Scott already mentioned, I think it's a mix of a few different things. We have a mix of software mitigations, for example, Red Pauline, where you insert some code snippets to kind of stop speculation or do some other things. Combination of microcode, so we add some new barriers and so on, for example, IBPB, and for example, IBRS that kind of separates, make sure that ring 3 can't control the targets that are selected in ring 0. And yeah, of course, newer hardware has some in-hardware mitigations, but yeah, it's always kind of a trade-off here. You have software, U-code, hardware that needs to cooperate, basically. Besides that, there's a few other mitigations, IBT, which enforces that indirect calls just target a certain instruction, an end branch instruction. I'll also get to this in a bit. And as Scott already hinted at, we have a bunch of these kind of knobs that you can tweak in this II32 spec control model, specific register, where you can disable certain behavior so that branch history isn't shared between different modes, between ring 0 and ring 3, for example. But the take-home key message here is that all these mitigations, they have some kind of performance trade-off. Like some of them don't have a high performance overhead, some of them definitely do. So once you enable all of these, you might end up with quite a significant performance overhead. That's kind of the point I want to make here. So let's go into have a look at what a Spectre exploit looks like in practice, how an attacker can actually exploit these things to steal confidential information. So we're talking about the speculative world here. So it's stuff that the processor runs that's never really architecturally valid, but it leaves some kind of microarchitectural trace that can be detected later. So typically you start the speculation, you or some confused deputy, for example, accesses some speculative data, some confidential data, and then which leaves a trace in some microarchitectural trace, for example, in the caches, and then the attacker leaks it through something like a cache attack. So as an example, here's an example of how one of these attacks could happen in practice. So you have an attacker that trains the branch predictor so that a certain call site will speculatively target a gadget of their choosing. So they do this train this in user space, and they have a previously selected gadget that is in the kernel, like a virtual address in the kernel where they know a gadget location that does something that leaves an microarchitectural trace. They trick the kernel into doing something, doing an indirect call, which they have previously trained the branch predictor to actually speculatively execute the gadget of their choosing. And then later they kind of can time the caches, do a cache attack, and see whatever this gadget speculatively accessed. So, for example, a cache attack, you would go through a certain known buffer, you time all the accesses. If one of them is slow, you know that this has been evicted by the gadget that the kernel executes for you. And then you know what the value is. I'll give you a more detailed example here for the speculatively example I have here. So here you have an attacker training a branch predictor, just a for loop that calls indirect call. You train the branch predictor to do a certain mapping from one indirect call site to a certain gadget of their choosing. The victim in this case is the kernel, so the attacker does a system call, which at some point will do an indirect call, where the attacker has control over RDI and RSI, for example. So two registers that the attacker can control, which is quite typical in a system call, right? You have the attacker can choose control the arguments to the system call. So what will happen is that this indirect call in the kernel will speculatively execute the so-called gadget, the gadget of choosing by the attacker. Here's an example where the attacker controls both arguments. So first one is int L, the length, or rather the offset that's going to be used in this gadget, and some kind of pointer, for example. So in this example, we see that what the gadget does, it has some arbitrary kernel pointer called kptr here, accesses an offset of it called L, which the attacker controls. So the attacker can basically read some arbitrary offset from this pointer, which is the secret, right? This is the secret data the attacker wants to steal. This value is then stored in some register, for example, and later there's a dependent access dependent on the secret, which somehow aliases one of the buffers that the attacker controls. So basically what this does is leaves a detectable microarchitectural trace, in this case in the cache. So basically what can happen here is after this gadget is executed, the attacker can go through one of these setup buffers that contains some cache sets. And basically loops through the whole thing and then times the access for everything. So in this case, we have a fast, then we have a slow one which was evicted by the target gadget. So we know that the secret value that the attacker wants to steal is 2 in this case. So yeah, this is an example of how these kind of attacks work. Of course, this glosses over some of the actual requirements for setting up the cache attack and so on. But in general, this is how these kind of attacks work. So yeah, the point here is that we see that, okay, the secret that we can steal is leaves a microarchitectural trace that is detectable by the attacker. So as I mentioned, speculatively had a bunch of mitigations, right? So we had IBRS, which kind of makes sure that you can't train the branch target buffer from user space. So some people here in Amsterdam came up with a new variant of Spectre to circumvent these kind of mitigations. So yeah, IBRS disallows BTI from a lower privilege level, but then the question is, okay, what other things can attacker still control? Turns out there's this branch history buffer that kind of determines the tag that looks up the target for indirect call. So by controlling the history of calls that have been, the branches that have been taken historically by the CPU, can actually determine what the speculative target is of an indirect call, which is kind of nice. You have some control. Well, nice for an attacker, not from a defensive perspective. So the attacker can control, if there's some targets in there, they can control what the target that indirect call will speculate to. And one note is that it only works in practice for early indirect calls in the kernel, because if you're in use space, so it has the history, at some point, if you have a bunch of other things going on in the kernel, the branch history buffer will be filled with whatever is in the kernel. So yeah, in any ways, there's ways to, like, it's kind of, you have this bunch of ways to circumvent the mitigations that are in there. So here, for example, is the example what can happen. You have an attacker that does a bunch of different function calls, which massages the branch history buffer, and then when an indirect call happens in the kernel, it will speculate to whatever tag the attacker crafted with this history that they created. One other background thing I want to mention is CET-IBT, for what Scott already mentioned, so Indirect Branch Tracking. This is a hardware feature that was enabled for Intel CPUs quite a while ago. And what it does is that it makes sure that every indirect call needs to target an in-branch instruction. So it's an opcode that you need to have at the beginning of a function that it targets. So, and otherwise, you get a fault if you don't have this thing in there. And the nice thing is that it limits both the architectural and the speculative targets to in-branch targets. So, suppose, yes, well, it limits, it doesn't, yeah. So, what we do is, for example, we have here, we have a caller that does a call, and an indirect call. So you see it here at the top, like we have a caller that moves some kind of target function pointer into R11, moves some value into RDI, the first register, and then does an indirect call. So yeah, for valid target, if we have IBT enabled, the target needs to start with the end branch instruction. So in this case, we have a function called valid target. It starts with the end branch instruction. If you do this call, it's all fine. If you have another target that doesn't have it, architecturally, like if you jump to a gadget, it will fault. Speculatively, it's also supposedly shouldn't really take that one. So yeah, the nice thing about this is like eliminates quite a large part of the attack surface for like both architecturally and microarchitecturally. So yeah, as you may see here, like if there's a missing end branch, you will get a hardware fault, which will trigger fault, and so it's detectable that something weird is going on. Some control flow hijacking has happened, most likely. Yeah, if you have another gadget with an end branch, though, you can still jump to that, right? So IBT by itself doesn't really prevent any specific, isn't really a full CFI solution. It just looks at whether there's an end branch instruction there. Which moves us to the next point is what Spectre gadgets are there still remaining in the kernel then? Like we have IBT and so on, right? So we can limit whatever targets an indirect call has. Well, the thing is, an indirect call, it doesn't really know about, doesn't really have a concept of function type or how many arguments a function has. So as I showed you in the previous example, you can, like if you have an indirect call, as long as they're in branch with IBT enabled, you can actually, you can target that. So suppose you have an indirect call that is supposed to target something like a function that takes one integer argument, right? So that's fine. But speculatively, like even if you have the end branch, you could like speculatively jump to one of these other things with a totally different type definition. And the problem with this is that we could have a gadget that actually uses some register, right? So if you have only one register, controllable, like the meant target site with one register, okay, it's fine. But suppose the attacker controls two registers, and you speculatively execute one of these gadgets where the attacker can actually has more control. It kind of enables us, gives the attacker a lot more gadgets that are possible, right? So the key insight is that we kind of want to limit the targets of indirect calls to kind of a known valid type. So so that it doesn't speculate to any arbitrary things that can do all kinds of weird things in the kernel. So basically, there's many ways to hijack speculative control flow through indirect branches. It's been kind of there's been a bunch of ways to exploit it. There's been a bunch of mitigations. IBT improves the situation significantly, but yeah, there's still, as I showed you here, there's a bunch of gadgets left, right? If you can just pick any function from the kernel, it's kind of a big attack surface to choose from. So we need some kind of principal mitigation to prevent, like, to at least limit the amount of gadgets available for an attacker in the kernel. And finally, I want to mention, as I already mentioned, there's been attacks mitigation. It's kind of a cat and mouse game. There's been so many papers published about this, new papers coming up all the time. I think a lot of these things are, some people that are here in the room, and you can go follow the highway to one of these buildings at the university, and you have a bunch of PhD students coming up with new attacks all the time. So yeah, if you're interested in this material, want to have some more in-depth knowledge about it, I can highly recommend these papers. Some of them are definitely not light to read, but they're very interesting. And Scott will now tell you more about our FineIBT solution.
I'm curious, show of hands, who has heard of FineIBT before today? Okay, anyone in the back? Anyone in the back too? No? All right. I hope when Sebastian and I come back here in 5 years, we'll see at least 90% of the hands raised. That's when we'll know that we and Peter Zelstra and the rest of our team have really done our job, but we shall see. I think that the last time I scanned the Linux kernel, I found tens of thousands of unique indirect call targets. And if you have tens of thousands of unique indirect call targets, CET-IBT on its own, while it might be a necessary component of a mitigation, will not be a sufficient component of a comprehensive mitigation, because there are so many different choices for end branches that you might select for a given call to do something nasty. And that's why we have FineIBT. Now, FineIBT is a software technique that builds on top of CET-IBT, and it's not very complicated. I'll walk through the assembly. At each indirect call site, so you can think of this as anywhere where there's a function call through a function pointer in C code, the compiler will take a hash of the function pointer's type. It's a 32-bit hash, and will inject an instruction to move that 32-bit hash into R10D, so the lower 32 bits of the R10 register. And this is a behavior that's actually inherited from another related feature called KCFI, kernel CFI, that is a pure software solution, does not rely on CET-IBT at all, but FineIBT is an alternative that binds a software technique to a hardware one. And then the call occurs. And if it lands on an end branch, so if it doesn't land on an end branch, then you get a kernel panic. But if you do land on an end branch, now you're subjected to an additional check. So there's the coarse grain check performed by the end branch. Then there's a fine grain check performed by FineIBT. And that also has a 32-bit hash that was injected by the compiler, and it is a hash of the call targets type. Now, if the two hashes are identical, meaning that the types are identical, modulo the possibility of a collision, which I'll talk about. If they're identical, the result of the subtraction will be 0. This JZ, jump if 0, will activate, skip over the undefined instruction, and go into the function. If the hashes do not match, the JZ will fall through and cause an error. So this is the coarse grain check, then the fine grain check, and that's the solution. So what about hash collisions? So I mentioned there are tens of thousands of unique indirect call targets, but the hash is not produced by the call target, it's produced by the type of the call target. And there are only about 11,000 unique indirect callable function types in the Linux kernel as of the last one I scanned, which is maybe 6.11, so not so long ago. And if you have a 32-bit hash width, then the expected number of collisions you'll have throughout the entire kernel is about 0.01. So we're not especially concerned about hash collisions, but someone always asks that question, and so I figure I'd be up front and try to preempt it. So that's how FineIBT mitigates architectural vulnerabilities, your classical cop attacks. But can it also mitigate microarchitectural vulnerabilities? And the answer is not right out of the box, because the mitigation itself introduces an additional conditional branch, the jump of 0, and that can also be predicted by the processor. Therefore, it can also be mispredicted by the processor. So if it's mispredicted, if both the indirect call and the JZ are both mispredicted, then you could have a possibility that on the microarchitectural path, on the speculative path, you could execute the contents of a function after a type mismatch. And that could allow a gadget to be executed, and that could allow a potential data exposure. So the solution that we introduce with FineIBT plus BHI, which is what we've chosen to call it because it was originally conceived as a novel mitigation to address branch history injection. There's a historical aspect to that name. The solution that we've adopted is to use cmove instructions, which on X86, unlike the jump instructions, are not predictable. We use the cmove instructions to poison the registers that are live at the call target if the hashes do not match. So suppose that the indirect call was mispredicted and the jump was, the JZ was mispredicted. If the JZ was mispredicted, that means that the hashes did not actually match. So the outcome of the subtraction was not 0, and therefore the cmove NZ will activate, and it will poison the live register, in this example RDI. So in the X86 ABI, RDI would contain the first live argument to a function, if the function takes at least one argument. So the contents of that register, which might be attacker controllable, is overwritten with the residual of that hash check. And there are a couple neat properties. So first, in X86, which has lots of fun properties because of historical reasons, because of backwards compatibility, if you perform a subtraction, addition, whatever arithmetic operation on the lower 32 bits of a general purpose register, it automatically clears, it zeros the upper 32 bits. So R10 will be some have some value, some non-zero value in its lower 32 bits, and the upper 32 bits will all be zeros. So why is that significant?
It's a user space address.
Yes, Peter Zelstra is correct. It's a user space address. And Linux has also adopted, what's the name of the feature that prevents kernel mode from reading user mode?
KPTI?
No, not.
SMAP.
SMAP, yes, SMAP, you reminded me, thank you. SMAP, Supervisor Mode Access Protection, I believe. Yes. So any pointer, any attempt to use a pointer in the kernel with its upper 32 bits set to 0 will not yield any data. That instruction will not result in a load occurring.
Result in a trap.
Yes, it will result in trap. And the lower 32 bits also will be written with the result of a difference in two immediate values, so the hash at the call target and the hash at the call site, and those are not attacker controllable. Those are just immediate values in the instruction stream in the binary. So we take the attacker controlled data, override it with something that is constant and cannot be used as a pointer in the kernel. But there are some challenges that we have to overcome to get this to work properly. So the first challenge is, how does the kernel know how many registers are live at the call target? How does it know how many registers it has to poison? So we had to upstream a small change into LLVM Clang, And that change was to endow the compiler with the ability to annotate within the kernel binary each function's arity, the number of arguments that it takes. And we found a convenient way to do that. So KCFI, when enabled for the compiler, it causes the compiler to produce those hashes. And the compiler just writes those hashes into a little 16-byte prefix before each indirect call target. And it just happened to use this instruction. It would move the immediate into the EAX register. That instruction would never actually execute. It was just sort of convenient to give the kernel some place to read the hash when it needs to patch in KCFI or FineIBT. And we looked at that and said, oh, that EAX register, that's encoded by 3 bits, and we really only need 3 bits to encode the arity of a function. So we're going to introduce a mapping, and we're going to endow that register with new meaning, and that's going to indicate the function's arity. So now when the kernel boots up, and it realizes it's going to need to use FineIBT plus BHI, it will interpret that register to indicate the function's arity and determine how many registers need to be poisoned. So that was a neat little trick. That wasn't the only challenge. The second challenge is that I'll ask the question first. Is there actually enough space in that 16-byte prefix before each function to actually stick in these C moves to poison the registers? So let's try this. I'm going to count up the number of bytes, and we'll see if this actually works or not. And maybe some of you can help me. I'll help with the first instruction because I would not know if asked out of hand that how many bytes the N branch 64-bit variant consumes, and it's 4 bytes. Anyone happen to have an idea how many bytes subtraction by a 4-byte immediate? 7. Yes, very good. It's so funny, yeah. You give the same talk at Intel, and it's like an audience of trained dolphins jumping up and down that say, "Oh, mod RM byte, you need the Rex prefix." Yes, 7 bytes, and then the jump 0. 2, yes. Jump near with a short distance is 1 byte, and then you need the 1 additional byte. Yes, you're spoiling it for me, Peter. And then the UD2 is 2 bytes, and then do you know this one, Peter?
The C move? This is 4.
Yes, it's 4. Yeah, 2-byte opcode. 1 mod RM byte, and again, you have these extended registers that are part of X64, and that adds another byte. And if we add that up, we get?
More than 16.
More than 16. We get 17 bytes. Oh no, looks like we can't do this. Well, actually we can. We use a neat trick, and it involves this strange thing. Yeah, what is this? This is jump if not 0. We changed the jump 0 to a jump if not 0, and we no longer have a label. Now we're jumping backwards by 7. So the way this works on X87 is that the immediate after the jump is actually taken into account after the jump executes. So starting from the next byte after jump, you subtract 7 bytes, and then that lands you somewhere within the sub instruction. And if you count 1, 2, 3, 4, 5, 6, 7, you actually find that you land on the 3rd byte of the subtraction instruction, and that's EA. And so what is EA? Well, I don't know if the resolution would actually support this experiment. No, it probably wouldn't. Laptop resolution is much better than this resolution. Yeah. If you look at the opcode tables in the software developer's manual from Intel, I think the AMD one, it kind of shows up. Yeah. It kind of shows up. And then you'll have to click that back button, otherwise it'll fling you back to the beginning of the presentation. Yeah, so if you look up E and then A, you'll actually see that this is far jump. Oh, far jump, that sounds wild. That sounds terrifying. Why would we use a far jump? Actually, because far jump is not defined in the 64-bit architecture. It's a 32-bit only. And so that UDs. So it's effectively kind of the same thing as using a UD instruction. But it's already there in the sub-instruction, so as long as it's already there, we can use it. Okay, thank you, Sebastian.
Well, so the Intel architects disagreed.
They did. Yeah, okay, there was another disclaimer I was supposed to issue at the beginning that all the examples are from what you'd see currently as of the 6.15 kernel. We're constantly making tweaks. Maybe Peter could talk about them afterwards in the Q&A. It's always been interesting. We're always learning new things by writing overlapping instruction sequences, but I'm going to move on. Oh yeah, so then the next question is, what if there are more than one live register? Well, then we need at least 2 C moves, maybe 3, maybe 4, maybe more, and we certainly can't perform enough instruction trickery to fit more C moves into 16 bytes. But you'll notice that with this new sequence, at least we're not even at 16 bytes, we're at 15 bytes. And so what we can do is we can take that C move out, and instead we can put in a near call, and the call is 1 byte, and then you can have a near immediate operand that is 4 bytes, and you can call one of these little stubs, and we've got one of these for each functionality. And so if you've got a function with 2 arguments, then there's a stub that's defined somewhere in the kernel in assembly that has 2 C moves in it that poisons the 2 argument registers. And then so on, 3, 4, and then if you're passing arguments on the stack, it will also poison the stack pointer. And how about performance? How does this actually perform? Is this bad, good? Sometimes it's hard to know, but we can actually do a little bit of back of the napkin analysis. So let's do like a little exercise, and suppose that this function that we are hardening with FineIBT plus BHI, the first instruction that it's going to add that's going to perform in the function body is this add instruction. So it's going to take the pointer argument, which was provided in RDI, and it's going to use that as one of its source operands. Remember, this is Intel, so we go from right to left, so RDI is the source there. And their back of the napkin analysis is going to ask, how much longer is this add going to have to wait to execute because we're doing this C move poisoning trickery? Well, we've got to look at the dependencies, because that's how modern superscalar architectures work, is they track dependency chains, and they execute instructions in parallel and out of order. So add's nearest dependency is the C move, and on most Intel processors, C move has a latency of 1 cycle, so that adds 1 cycle of additional weight. And the C move depends on R10, and the most recent dependency that defines R10 is that sub-instruction, and then before that there is the move instruction, and that move doesn't have any more dependencies because it gets its only source operand from the instruction stream. Now there is another dependency, it's the original definition of RDI, but that would have been there with or without, that you would have had to pay that cost with or without FineIBT plus BHI. So the answer is that FineIBT plus BHI will make that add instruction wait an additional 3 cycles. But 3 cycles is sort of meaningless without any context. So if we compare this to some of the other hardware mitigations that Sebastian mentioned earlier, some of them will cause more mispredictions to occur. And mispredictions are quite a bit more expensive than 3 cycles. And I think that on most Intel processors, a misprediction penalty on its own, before you take into account having to re-execute instructions again, that the misprediction penalty on its own is 15 to 20 cycles. So this is certainly much cheaper.
Yeah, I think like Reptiline, they force a misprediction.
Yes, Reptiline is not a good poster child, to say the least. Glad we've at least moved past that for the most part. All right, and now Sebastian is going to give us a more empirical analysis of some of the early benchmarking we've done.
Yeah, so we've done a bunch of benchmarking on this setup, right? So what we did is we looked at different microarchitectures because, yeah, Scott showed you this calculation of like how many cycles it takes, but yeah, it might depend on the microarchitecture, right? How this behaves. So basically, we picked out 3 representative microarchitectures. One 14-gen core, also known as Raptor Lake, which contains both E cores and P cores. Our server platform, so the Granite Rapids, which only has P cores, and then the Arrow Lake desktop computer, so the Core Ultra Series 2, which also has newer E cores and newer P cores. So what we did is we run a bunch of benchmarks. We ran Phoronix OS benchmarks and Unix bench. There's some variance in there, but so in my opinion, the most representative one is the Phoronix OS benchmarks, which is a huge set of a bunch of real-world workloads. And what we can see here is, in general, the overhead with FineIBT plus BHI is negligible compared to FineIBT. With the asterisk here is that these setups are ones that we consider equivalent from some kind of equivalent from a security standpoint. So the FineIBT setup has default mitigations on, so BHI dis-S is enabled, which currently Ubuntu has it enabled by default, even with FineIBT. With FineIBT BHI, we're confident in that we don't need the mitigation, the BHI dis-S, so we can turn it off. So the nice thing is, for example, on Arrow Lake, we actually get the performance speed up, even despite the C moves that we have in there. Granite Rapids, it's equivalent from what we can see at the moment. We have some micro benchmarks in Unix bench that I haven't included here. In general, what we can see is adding the C moves is also, even with the BHI dis-S turned on or off, we can see that it's kind of negligible on a lot of microarchitectures. So conclusion is that I think it's worth to have something like this, right? It's a very small performance overhead, like in the order of like less than 2%. Most of these, like the difference is like lower than 1%, which is actually, it's kind of a nice result, like even for, considering adding an extra call and C moves and so on in there. So if you have any questions about this, feel free to come up. We have done a bunch of more benchmarking, but this is the one we're showing here at the moment, which I think is quite representative of the overall system performance. And Scott?
I think that the two of the 3 you showed were actually negative overhead, right? Negative overhead of
yeah, so like FineIBT BHI, we have a better performance with FineIBT.
Right.
Yeah.
Okay. All right. This is the slide we showed at the beginning because this is, as I alluded to in the beginning, this is a work in progress. There's still work to be done. Yeah, but this is eventually the goal, is that we're going to have FineIBT plus BHI as the forward edge CFI solution for Linux, for the Linux kernel, on Intel processors. And the one aspect that we're working on right now is that currently FineIBT, and therefore FineIBT BHI, depend on KCFI, which is that software-based CFI solution that is hardware vendor agnostic. KCFI has been implemented for some time in the Clang tool chain, but has not yet been upstreamed into GCC. Yes?
So Case Cook posted patches for GCC a week ago.
Oh, that's news to me. Thank you, Peter. All right. Skies are already looking a little sunnier. And there's some additional caveats that we're also trying to work through. So one is that some of those hardware features that Sebastian detailed in one of the earlier slides are required not just to enforce forward edge microarchitectural CFI, but also backward edge microarchitectural CFI. And that's only true for some Intel processors, not for all. But we're trying to work to make sure that in the future we will be able to safely disable some of those if FineIBT plus BHI is deployed, because then they would only be required for the forward edge CFI and not for the backward edge one. And another question that we often get is, What if there are two indirect call targets with the same type, therefore they would have the same hash, but they actually behave very differently? And something malicious could happen if you cause a redirection from one of those targets to the other one. So a simple example is, think of something that's not so uncommon in the Linux kernel, somewhat unfortunately. You have a function with one or two arguments, and one of them is a void pointer. And it gets cast into a wildly different type in one function versus the other one. And at least theoretically, you could concoct a malicious gadget, but are there actually such gadgets that exist in the Linux kernel? So there were a couple researchers at Tel Aviv University who studied this question, and this was several years ago. They published their results in Usenix, and they asked this question along with several others. At that time, they didn't find any evidence in the Linux kernel. We also conducted our own internal analysis. We used a different approach, different tool chain, and we also did not find any evidence that this kind of speculative type confusion could actually be exploitable. But that's something else we just want to be upfront about. And finally, just to reemphasize the main point, why Sebastian and Peter and myself are here today, is we would like to finally replace the numerous and often hard to understand various hardware approaches for enforcing forward-edge fine-grained CFI with a single unified solution that provides architectural security and microarchitectural security, and simplify the job, not just for us, but also for the Linux community, who I hope would appreciate what we're doing. Sebastian and I, and Peter Zelstra and myself, we'd like to thank you for being a patient and terrific audience, and thank you for being a terrific security community. Thank you.
Thanks.
Questions?
Hi, I agree that the chances of a hash collision are extremely low. Have you considered salting the hash anyway with a unique salt at the beginning of each kernel boot, and then you pretty much remove that concern at all?
I believe Linux already supports that option. Yeah. Peter might know more. Yeah, I think, yeah, you can take
Come
it.
up. Yeah.
Yeah. Hi. So I wrote all the code. They concocted the ideas. Yeah, so we rehash all the hashes. Additionally, there has been work into looking into an LTO pass that does whole program analysis to differentiate hashes that or function targets that hash the same or have the same prototype but are not actually used interchangeably, like from file system. For file system, sorry, operations like and for example scheduler indirect calls, they could have the same prototype, but they'll never mix. Things like these can be detected in an LTO pass, and then the hashes can be adjusted. That's future work. It's not actually implemented, but it could be done. Joao did some work on that, but I think sadly he left Intel, didn't he?
Yep.
Yeah. So those are things. Andrew Cooper also asked for explicit function attributes to manually annotate these things. That's also on a to-do list somewhere. So yeah.
Other questions?
So this might be a stupid question. When we restrict the possible branch targets to the real categories of functions, how many gadgets would remain that can be exploited?
This gets to the speculative type confusion question, I think, and at least the answer that we've found, I should be careful how I phrase this. We have looked for evidence that there are still residual gadgets, we being Intel and also some external researchers, and neither we nor external researchers have thus far found residual exploitable gadgets.
The ones we found, we killed.
Summers.
Yeah, I had a few questions. Let me think. So maybe first of all, the far jump in the middle of the sub, does it actually also microarchitecturally have the same effect as a UD2? Like, at some point it will crash, but you want also microarchitecturally that the stream stops, right?
Yeah, it's a single byte UD instruction.
Okay.
However, the Intel architects were not well pleased that we've used this because it's actually on the reserved opcode list. They want to have it reserved for future extensions. So Peter Anvin did the committee juggle and got a single byte UD instruction approved, which will be D6, and it will be called UDB in the next SDM. With that information, I had to rejig this entire scheme, and I have a patch out, and I shall post it again next week-ish, that basically does the same thing as presented, but radically different instruction setup.
So, and maybe why wouldn't you just, now you jump back 7 bytes somewhere in the middle of the sub, but inside the sub there's 4 bytes of immediate, right, that you control. And right now you're using some hash, but all you want is just a set of unique identifiers, right? So if you only need 11,000 unique identifiers, probably 4 bytes is way too much, and you can put a byte in there that is your opcode.
So that puts more constraints on the compiler. But yeah, so what we've done, what I've done is not shown in these slides is that every function also starts with end branch. So the prefix starts with an end branch, but the function also starts with an end branch, and that end branch is poisoned with an op4, mostly. What I've arranged for is that an op4 that has an immediate, and that single byte immediate will be the D6. So then we'll jump into the immediate of the op4. That is the first 4 bytes of every function. And then because of the BHI thing, that whole preamble was too big. There were some more gimmicks that Scott didn't talk about, but to make it fit, Peter Anvin suggested using RAX register instead of R10D, or EAX. Because EAX is the accumulation register and has shorter encodings on x86 64, and with that trickery we'll get some extra bytes and then it all fits again. So yeah, the whole thing is rejigged, but it'll basically do the same thing.
Okay, so I guess the conclusion is you can make the puzzle work.
Yeah.
Maybe, can I do another question? So I guess the obvious question that's been left untouched is what is the speculative window you get from jumping to not an end branch?
So the SDM says 0.
It varies by part. So some of the very first parts with CET-IBT, I'll have a small window.
Tiger Lake was particularly
Yes. Well, that was the first part, the first processor family with CET-IBT. And then I think the next generation had a much smaller window. And then the next generation after that had either, I believe, had no window. So I think on the brand new processors, there should be no window.
Yeah, so the E-cores have always had 0.
So as far as I remember, the E-cores, all of the E-cores that support IBT have a 0 window. The P-cores were the ones that had funnies. And like I said, Tiger Lake, that was the very first that supported IBT, that had a fairly large window. And after that, it's been successively improved.
And does this take, like, was there some engineers that took into account an attacker really trying to make the best out of it? So I never tried anything like this, but maybe like trying to poison the micro-op cache to make it think that there is something valid there while it's actually like think that it's an M branch there while there's not, or things like this. Like, I don't know how do you test a window of zero? Is that like a proof of like that, you know, okay, we checked cycle by cycle on the processor and we know for sure nothing can happen? Or is it someone did some tests and we measured the window to be zero?
We conduct internal validation, and the aim of that validation is to support claims that we make. There could always be gaps, and if there are, I suspect that someone will find them and notify us, and then we can publish guidance accordingly.
Okay, yeah. So that doesn't really answer my question, but
As far as we know, it's really zero.
okay.
Yeah, I think we would need to get an architect in here too, but they probably wouldn't be able to answer it anyway. So like it's
Even if they knew, they wouldn't
Yeah.
know what to say.
Yeah, it sounds like a very tough question to answer. That's why, yeah, zero sounds very confident. But okay, thank you.
Thank you.
Other questions?
So would it make sense, instead of using the jump and the poisoning, to have some sort of architectural way to say, if this FineIBT check fails, I stop speculating at once and poison everything?
Could you clarify what you mean by some architectural way?
Define a new instruction for new processors that we can use if we just target new CPUs?
Yes, I understand.
So have a long-term solution then.
Well, see, you can only imagine so much that can go wrong. It's risky to define new instructions for security based on today's assumptions. And this approach is very inexpensive for performance, because you're injecting the hashes into the instruction stream. It's just not very expensive, and it gives us a degree of flexibility to maneuver in the future if it turns out one of our assumptions is incorrect. Once you take all the assumptions we have today and bake them into an instruction, and then an assumption changes, it's tough. I think we're satisfied with this solution right now, and we like the degree of flexibility that it offers.
More questions? Okay, let's thank the speakers again.
yes.
Thank you.